Okay. All right. Hello, everyone. Very excited for the very first seminar of this semester. Welcome everyone to the UW-Platteville Engineering Seminar Series, both in person and on Zoom. My name is Danny Shaw. I'm your host today. So let me introduce our speaker, and for the first time, I want to introduce the company as well, because we're sponsored for the food. So thank you very much, Terracon. So I want to introduce the topic: advantages of deep foundation testing in bridge construction projects. So very exciting. Going geotech and also bridge, right? So I'm not going to read the abstract here. We'll leave for the speaker to give us a wonderful presentation. But the speaker here, Mr. Rob Kramer, has worked for Terracon for over 15 years. He's a regional service manager in charge of geophysics and instrumented service. And we were just talking about the degree. Rob got degree from in physics and math. Perfect background for what you're doing here. Awesome. So Kramer helps Terracon project managers and clients better understand subsurface site conditions through geophysics and related technologies. Again, we want to thank the sponsorship from Terracon. Terracon is an employee-owned, multidisciplinary engineering consulting firm founded in 1965 with more than 6,000 employees in 175 offices nationwide. Our engineers, scientists, architects, facility experts, and field professionals are focused on solving engineering and technical challenges on your upcoming project. Terracon was named a top 20 design firm by Engineering News Record in 2024. So without further ado, please help me welcome our speakers.
Yeah, so I'm Rob from Cedar Rapids, Iowa, geophysical services manager. So geophysics is a very broad umbrella at Terracon, but we'll be talking today specifically about deep foundation testing, which is kind of a niche topic, but something that I feel strongly about. We feel strongly about as a company. We'll talk about the advantages and originally was going to focus more on bridges, but I understand have a wide array of engineers here. So broaden that to just kind of general construction projects. Start out. This works.
Maybe it's because of the mouse. You move to the screen, maybe it will help. Then it should work. This isn't working. Click the presentation. Yep, now try it. There we go. Yep.
All right, so it is National Engineers Week. We do a lot at Terracon for National Engineers, so I wanted to just address everybody. Congratulate y'all. You're doing good work. You're entering a good industry and career field. I and everybody that I know loves working in engineering. So just to encourage you guys, you're doing good and you're heading down a good path. So get started here, just an introduction of what this presentation, what this talk is going to look like. We'll start with, what is a deep foundation? So I understand there's some geotech focus here. There's probably some structurals, but you may not all understand some of the things I'm talking about. So forgive me if I talk below some of you, and forgive me if I'm not technical enough for those of you that are familiar. But we'll talk about what is a deep foundation, what is deep foundation testing, and why is it important in construction and in this process. And then throughout some of the examples, I will have some case studies and just kind of project examples that demonstrate the importance of this deep foundation testing. All right, so to get started, a little bit about Terracon. Danny introduced Terracon a little bit, but Terracon, we're engineers and consultants, 4 main service lines that kind of span the entire project lifecycle from the very, very beginning stages of a project to the very end where we're involved on the construction side. Our 4 service lines are geotechnical engineering, environmental engineering, materials testing and engineering, and then facilities engineering. So geotech and environmental very, very early on. Materials testing is happening during construction, kind of verifying the plans and the specs. And then facilities engineering is happening on existing facilities. that have maybe been around for 100 years and are going to be repurposed. So the deep foundations here that I'm talking about today are mostly involved with the geotechnical engineering and the materials testing and engineering. So on the geotech side, for those of you that aren't familiar, we're looking at the soils, we're designing foundations, we're making sure that the foundations that we're building on and the soils we're building on are going to be suitable, and we're not going to end up with a Leaning Tower of Pisa type situation where the building is tipping, foundations inadequate for the loads being applied, right? So foundation testing is important on the geotech side, because we want to make sure that what we're recommending is happening. And then it actually happens during construction on the materials testing side. So materials testing happens during construction where we're actually testing building materials, performing special inspections, and ensuring that construction is meeting the design requirements, right? So we recommend certain things happen. We want to make sure that they actually do happen on the construction side. So let's back up a little bit. What are deep foundations, right? And what types of foundations do we have? Well, there's two types of foundations, shallow foundations and deep foundations. I'm not going to talk too much about shallow foundations here, but typically shallow foundations are associated with your lighter loaded structures or structures that are being constructed on competent soil. So maybe resting on bedrock or you're not dealing with expansive clays or something that's going to lead to settlement. Deep foundations are typically heavier loaded structures, critical structures, or constructed on weak and incompetent soils. So what is deep foundation testing? Well, again, here a little bit more on deep foundations. Deep foundations are intended to transfer structural loads through weak soil materials to more competent underlying soils like rock, right, bedrock, in order to meet load carrying capacity requirements. Won't talk too much in detail there. There's an equation, side resistance or skin friction plus toe resistance. And the deep foundation here, the thing that I want to point out is it's a critical part of our construction of structures. Typically bridges, which I was going to focus on and kind of broaden that. But bridges, federal buildings, tall structures, hospitals, arenas, a lot of big critical structures rest on deep foundations. So foundations that transfer the load oftentimes down to a bedrock or a strong material below us. And deep foundation testing then is testing of those deep foundations. So oftentimes non-destructive evaluation of the quality, integrity, and real performance of these foundation elements. So why should you care? As I said, deep foundations are a critical element in your structure. They're also a really expensive part of your structure, right? Everybody cringes when we issue a geotech report that says it needs to be on deep foundations because it means you just added a lot of extra expense to your project. If you can get away with shallow foundations, you're going to save a lot of expense. So it's a critical part of our project, but it's also really expensive. So we want to make sure that this investment is important. Right, and so Terracom's been around for 60 years. This is our 60th year doing business, doing geotechnical engineering. And over those 60 years, we've been recommending deep foundations, and we have seen a lot of problems with the construction of the deep foundations that we recommend. Right, so here is a picture of a deep foundation. This is a drilled shaft. I forget if it was a 6-foot diameter drilled shaft. It was for a transmission line in Mason City, Iowa, so not too far from here, right? And we did the geotech, we helped design the foundation, and they go to put the pole on the foundation, and it immediately starts to settle and tip. They pull it back off, they set it down, they call us wondering what the heck, there's a whole bunch of fingers being pointed, what's going on here? We look at our report, we say there's no way that this thing should be settling. The structural engineer agrees that there's no way that this thing, it's over designed like everything. And so we get up there and we core, and 10 feet into the structure, we're no longer in concrete, we're in soil. And then there's a whole bunch more fingers being pointed, wondering how the heck did this happen? How did we not have logs? How did nobody recognize that there was only 10 yards of concrete being poured here when there should have been 30 or 40 yards of concrete? How did this slip through the cracks, right? And you'd be surprised. This kind of stuff happens way more than anybody would want to admit, right? Again, a critical structure, a very expensive structure, and this is the type of stuff that you end up getting. So we see that, we see discrepancies in logs, we get arguments over means and methods of contractors. Equipment starts to fail and you don't really catch it until it's too late or you're farther along in the project. And then just general incompetence of contractors. We get contractors that are doing this for the first time, they threw a little bit of the project and they're out there figuring it out on the fly, right? And you don't want that. So Terracon has taken a stance in the last couple of years that we're really gonna recommend this deep foundation testing. It's not really part of a code or a requirement, but we're gonna take a stance that says we're gonna recommend this. We're gonna recommend the QA QC part of this to protect everybody involved. The frequency of deep foundation testing can range from one test, a test pile or a shaft at the beginning of the project, to 100% of the shafts, depending on the risk of the soils you're building on, the risk of the structure. And it protects all parties involved, right? So if we're the geotechnical engineer, having some sort of assurance that what we're recommending is valid. It protects the contractor in case something happens down the road. They did some due diligence, they did some testing to ensure that their foundation is good and there was no flaws. And it maybe doesn't protect the owner as much, but it at least gives them some warm and fuzzy feelings that this thing that they're paying a lot of money for is a sound foundation. Types of deep foundations. First, we have drilled foundations. So shafts, piers, you've probably seen, if you've been around some construction, you've seen some drilled foundations. This is an example of a drilled foundation here. Auger cast piles, this is an example of some auger cast piles here. That's, you're drilling a hole and the augers are moving the soil. Then it's got a hollow center. You send grout down the center of that and it pumps up and you remove the auger and it fills the hole with grout, and then you put some sort of a cage or center bar in that auger cast pile. And then driven piles. So these are the three main foundation types for deep foundations. More recently, these three have been more popular, but they're newer, they're efficient, they're cheaper, and since they're a little bit newer to the more popular, there are lesser methods for deep foundation testing. So I'll focus on the three that are most common: the drilled foundations, driven piles, and then the auger cast piles. So deep foundation testing falls kind of into three buckets. And first is just quality inspections and monitoring. So that's just kind of hey, ahead of time, we're going to test the concrete. We're going to be there to create a log. We're going to verify that things are generally being done as planned, right? Stuff as simple as checking elevations, testing the concrete as it comes out of the truck, and then there are some tools for actually inspecting an excavation. The middle bucket here is where these two buckets is where I'll focus this talk. Integrity testing. So actually testing the integrity of the concrete or grout of an in-place foundation once it's poured. And then load testing. So once the foundation is in the ground, actually applying a load to the foundation, making sure that it's going to stand up to the load that it is designed to stand up for. So we'll start with this first bucket and hopefully breeze through this pretty quick, but the quality inspections and monitoring. So first is concrete and grout testing. So a drilled foundation, you have a material, right? So we're going to test the material. We're gonna be there when the truck shows up. We're gonna take a cylinder. We're gonna test the grout or the material. And there's three types of tests that can be performed. One is a slump test. That's right here, just to make sure that concrete is supposed to come off the truck with a certain slump. Then the second is a compressive strength test. So we take a cylinder, we keep that cylinder under certain conditions. We take it back to the lab, and then 7 days later, 28 days later, we break it, right? We put it in a machine, we apply a load to it, and we see how much load can be applied before that cylinder shatters, right? So if it's a 4,000 PSI concrete that's spec'd, we want to make sure that we can at least apply 4,000 PSI to this cylinder before it breaks. And then there's different things that they look at too, how the concrete breaks, what types of shatter will affect what happens on the back end if it breaks in a particular way. So these things are all performed though on the concrete that's coming out of the truck. It gives you a good sense of what's going into the hole, but you're not actually testing what's going into the hole or the actual in the field conditions, right? Because if you're pouring right now, it's very cold. That concrete is going to react differently than a concrete cylinder that is taken back to a lab in a controlled environment. Manual visual inspection. So that's just having somebody on site to visually see how things are doing, verifying means and methods, making sure that the contractor is not doing something stupid. And that's not surprisingly a requirement. So there are projects that slip by and contractors are just out there doing whatever the heck they want, and then you end up. This is just an example of, a driven pile being on site and verify the drive criteria, the hammer performance, create a log for either a driven pile or a drill shaft, right? Here's some of the stuff that we're going to want to be verifying and looking at in the field. So I mentioned a couple of devices. There's a shaft inspection device that can be sent down an excavation to make sure that if that shaft is end bearing, it's supposed to be bearing on a good flat, hard rock surface. Problem is when you drill that excavation and you remove that soil, a lot of times you end up with a muddy mess at the bottom of the excavation, and you want to make sure that that's clean. Decades ago, you would actually send a person down the excavation and they may clean it out or inspect it. OSHA has since said that we shouldn't be doing that. So now we send this shaft inspection device down and it measures that and makes sure that you're on a good hard rock surface and that there's not going to be a couple of inches of muck at the bottom of your concrete. And when you load that, it moves and settles, right? And then we have this shaft area profile evaluator is another tool that can be used to inspect the excavation before the concrete is placed. And that's just looking at the walls to show you the shape of the excavation. It can show you that it's plumb, that it was drilled straight, and that everything is as expected before the concrete is. Okay, so then we have integrity testing. So this is looking at the actual shaft once it's in the ground. Integrity testing is typically associated with drilled shafts or concrete or gravel. So your drilled shaft, your caissons, your auger cast piles, like that. So there's three main test methods that I'll focus on here today. There are a couple others that are rarer that are usually required in like California code for certain structures, but otherwise not widely utilized tools. We'll start with cross-hole logging. So CSL has been around a long time. It's a great diagnostic tool. It's well understood. And it's a tool that is used to identify or verify the integrity of a drill shaft. And what we're looking for is anomalies in the arrival time or relative energy, and I'll get into that a little bit more here. Big advantage to cross-hole logging is that it's been around a long time, and it's well understood and well studied. So there's an FHWA rating criteria. So highway projects, bridge projects, anything transportation related really likes CSL because it's got this rating criteria, and we can say that a shaft is good or bad based on this rating criteria. The disadvantages here is that we're really only measuring between two pipes. We measure between every tube pair combination here. But the tubes, especially this time of year when it's cold and hot and you got a hot concrete and a cold air temperature, we have expansion. And so you get a lot of debonding of the tubes. And so at the top of the shaft, particularly where it's exposed to air, you get debonding, you can't get a signal through. So the upper few feet of data is oftentimes bad. The assumption is that you're straight concrete between the tubes. And so a lot of shafts are designed with cross bracing. You can kind of see some cross bracing in here. Anything that goes between those tubes then is going to show up in the data and be a potential false anomaly. And then you can only test a certain size shaft. I don't like to go much over a 6-foot diameter shaft, but definitely not more than 8. And so you're limited in some of your larger projects that you're just not going to get signal across a large diameter shaft. So here's kind of how CSL works. We're sending a signal between the two tubes, right, from transmitter to receiver, and we're looking at the time that it takes that to arrive and the energy loss from what's sent to what's received, right? And so we're looking at this FAT or the first arrival time. And we're looking for changes from the bottom of the shaft to the top as we pull these sensors up. And if there's a defect like this, the signal's going to travel around the defect, taking longer to get there, or it's going to go through a weaker material, taking longer and losing energy. Right, so this is what the data looks like on a CSL shaft, we call this a waterfall. It's basically this 1D wave turned into a 2D representation from top to bottom, right? But what you want is a nice, consistent arrival time and relatively consistent energy from top to bottom. This shows you that the concrete is homogeneous from top to bottom. It's like it's expected. What you don't want to see is something like this, right? Where we get a velocity reduction, we get an energy reduction, and your waterfall looks like this, right? And there's different, we look at the percentage reduction to rate the anomaly or the severity of the anomaly. That's that FHW rating criteria that I was talking about. But here was a bad anomaly in this drill shaft, and we got out there and we cored it with our drill rigs. And here's, the concrete that came back from that material. Maybe not catastrophic to your project, but could cause problems. So in this case, we can help then identify, we can do some 3D modeling, identify where this area is bad. And then oftentimes they'll core 2 areas, they'll get in and kind of power wash out this bad material and then regrout it so that it's solid. So that's CSL. CSL is great. We've been doing CSL for a long time. More recently, especially in the last 5 years, but about 10 years ago, this thermal integrity profiling became an ASTM standard or an accepted ASTM standard. And that really, outside of transportation projects, has taken over for any concrete or grouted structure. And so the thermal integrity profiling is very simple. You have a series of wires that are zip tied to the exterior of your rebar cage. And every foot there's a thermal sensor. So it's taking temperature readings. Very simple. It sends, you hook up boxes, it sends it to the cloud. We can monitor it remotely. So it's cheap, it's effective. You can have contractors set this stuff up. And you can monitor as soon as the concrete is poured, you can start monitoring the shaft and identify issues early on if there are issues. The big advantage to the thermal integrity profiling is that it's not directly between 2 pipes or it's outside of the cage. It's the entire shaft. You're able to detect anomalies. The biggest disadvantage is it's newer. There's less research and understanding of how much of a reduction is a problem. And so we don't end up with a rating of a shaft that says it's good or bad or pass or fail. But you get a ton of information, which I can kind of show you, concrete cover, cage alignment, flaw detection. There's a lot of bulges, necking. There's a lot this can tell you. So you can sit down with your project and really determine what's going on with the shaft and correct means and methods so that the shafts end up as designed. So here's how this thermal integrity profiling works kind of in theory, and then we'll show you some data in practice. So the idea is, for those of you that don't know, when concrete is poured and it begins to harden, there's a chemical reaction that happens and it's going to get really hot. So internal temperature of a concrete as it's curing can be upwards of about 150 degrees. And so you end up with a distribution of temperatures in a shaft like this, where the more concrete there is outside of the thermal sensor, the hotter it's going to be, right? And so it's hotter inside the shaft than it is outside, where it's exposed to the soil, or on top or bottom where it's exposed to air or rock, right? So we can tell you by looking at the data, we can tell you things like cage shift. So if it's hotter on one side of the shaft than the opposite wire, it's cooler on one side, you look at opposite wires, you can tell where the cage is in the excavation. So is it centered like it's supposed to be, or did it get pushed up against the wall, which is fairly common. You can tell whether just concrete cover, whether there's a bulge or a neck, whether, where it is in this temperature, whether it's hotter or colder on all the wires. You can tell just concrete cover distribution. You can determine whether there's an anomaly, whether you have a soil collapse or just weak concrete, you have a void, contaminated concrete, I kind of mentioned. Again, cooler temperatures in a localized area are indicative of a flaw in the concrete. So here's what this looks like in practice then, this thermal integrity profiling. This is an auger cast pile, so a small diameter pile. Historically, we haven't really had a good way to test auger cast piles because the CSL, there wasn't enough. You were taking up too much space in a small diameter pile to have that tube. They didn't like it. There was no good way to test it. But now we can test with this thermal integrity profiling. We can test these shafts. Here's an example of a good pile, relatively even distribution of temperatures from top to bottom. You do always get this roll off at the top where it's exposed to air, and at the bottom where it's exposed to ground. But you can see this increase here where there was a bulge in the shaft excavation. Not a problem typically for bulges are usually good. Increased skin friction, usually not a problem. Here's an example of a bad auger cast pile. So you can see a lot of variability here. Our logs showed that there were some issues with the drilling of this shaft. The problem here was right here where this modeled area dips way down. So we called this the attention. We thankfully had budgeted for some load tests, which I'll talk about, but we did a load test on this shaft, and before it achieved the desired load, the shaft broke, the pile broke. So that was good. It actually, nobody likes to get that news, but it was good that we caught it before it was during construction, and then the loads were applied, and then all of a sudden you got a corner of your building that's settling and cracking, and you have a significant problem, right? Here's another example of just a drilled shaft where in this case we have a bulge here that shows up in this 3D model. And then at the bottom, we kind of have a soft toe condition. So at the bottom where we don't have good concrete at the bottom of the shaft. Here is another example, and I'll show you the cores on this one, but this is like that picture that we showed at the beginning, where you kind of wonder what the heck happened. And in this case, we know what happened. This was a kind of a case of incompetence, but in this case, it was a contractor that had been around doing this for 50 years. And he was adamant that we've been doing it this way for 50 years. We don't believe that we need to pump this and tremie it. The story was they came back after a long weekend, and what was a dry hole had filled up with water. And they were convinced, the contractor was convinced that they didn't have to pump the water out, that they didn't have to tremie this, which means you put a pipe down and you pump the concrete from the bottom and it goes up, right? They were convinced that they could just back a concrete truck up and pour the concrete in from the surface and all would be well, right? And they said, we've been doing this for 50 years. This is how it's done. We've never had a shaft fail us. It's like, well, okay, we're going to test it and we'll find out. And so immediately within like 6 hours, we knew, but this was 23 hours after the concrete was poured. We knew that the bottom of the shaft was not heating up, was not looking like it's supposed to. If you look at the temperature here, you know, we're at about 115 degrees throughout. And then by the bottom of the shaft, we're 60, 50, 60 degrees, right? That's not concrete. That's tap water temperature, right? So we got up there and we cored. Here's the cores from the good concrete. Here's the cores as it really starts to cool down. And hopefully you can kind of see where that starts to become real brown, weak and crumbly. And then the bottom of that shaft came up in bangs, right? It's not concrete at all. It's a mucky material. So a very expensive shaft had to be re-poured. I don't think they end up removing something this large. They just pour it adjacent and then use that shaft. But the good news was we fixed this at the beginning of the shaft, or at the beginning of the project. So we knew going forward then that no, if you have a wet hole, your holes, your excavation's wet at the bottom, that you're going to pump it and you're going to trim it, and your way is not going to fly anymore, right? So we're able to correct this early on in the process, and then what ended up being a almost 100-mile transmission line across the border of Iowa and Minnesota. You can feel good about the means and methods and that everything is good going forward. Here, I mentioned the shape earlier, but here's just another example of tip data next to the shape data. So here was the shape of the excavation. We knew that there was a soil collapse during the drilling. And we had this bulge, and that shows up there in the data for the tip. I just think that's a nice comparison. Pile integrity testing is the last integrity test that we talk about. The pile integrity test has been around a lot and is probably overutilized because it's cheap, but it doesn't tell you a lot. In my opinion, this pile integrity test should only be used, you know, if we're testing 10% of the piles or shafts on a project, Pile integrity test should only be used if you didn't have CSL or tip tubes and tip wires installed on a shaft, and there was a problem during construction, right? If there was a delay in the concrete truck showing up, and this happens where all of a sudden you have a 4-hour delay and you're halfway through a pour, well, you're likely to have some sort of latent material or a cold joint or some sort of an issue halfway through. So if you want to verify whether that's still good or not, then you can do the pile integrity test after the fact. Pile integrity test is pretty simple. It's oftentimes a black magic. People are like, what the heck are you doing? All you're doing is hitting a hammer on the top of this thing, and you got a sensor off to the side, and you're measuring, you get a response at the surface from that hammer blow. And then you also get a response once it goes down and reflects off the bottom of the shaft and reflects back up to the sensor. You get another response here. So we know the general velocity of a concrete. And so we can say then, okay, it traveled this far, and that's the approximate length of the pile. And so then that's what a good shaft looks like. You get a good response off the toe. Here, if you got a defect, if you have a void or an intrusion or some necking, if you get a response off of something before the toe, that's what you get there. So in this case, we saw 2 defects and still saw the toe, which is pretty rare. But it's a valid test, ASTM approved, been around a long time, pretty well understood. It's just there are much better tools out there, and we shouldn't be relying on this unless we think that there's a problem and want to verify that there's not. And we didn't do anything else. So the third bucket here is load testing. And so this is actually looking at the capacity or the load bearing capability of a foundation. We'll start with driven piles. So driven piles, actually we'll start with driven piles, but let's back up here. First thing when we're driving piles, first thing we do is a wave equation analysis of the pile. And that's a theoretical drivability that's done, theoretical drivability analysis that's done where we look at the soil conditions, we look at the hammer that the contractor plans to use to drive the pile. We look at the pile size and we determine whether we can achieve the capacity that we are supposed to achieve. So for those of you that have never seen a driven pile, it's kind of a cool operation. If you have, you've driven out and you've seen a big crane up in the air and these big piles sticking out of the air and it's just going boom, boom, boom. It's real loud and there's smoke, coming off the hammer. It's a cool operation. But that's what's happening here is we have a pile, and instead of drilling a hole and filling it up, we're driving the pile into the ground. They can be steel, concrete, timber piles, but we're driving this pile into the ground to meet some sort of capacity. So the first thing we do, like I said, is this theoretical, and we're verifying that the hammer is going to be able to drive the pile to capacity without damaging, right? And that the soil conditions are going to get us the capacity that we want to get. So it's all theoretical, and a lot of times we tend to rely on this weep analysis too much. And I'll show you some examples here of where that weep has failed. So we perform the weep analysis, and then what we can do and should do is perform a pile driving analysis, and you can perform that on a certain number of piles throughout the project. If you want to section your arena off into quarters and you do 1 pile per quarter, or you do 10% of the piles randomly, or critical foundations that are carrying heavier loads that you want to make sure are good, you can do the pile driving analysis. But the pile driving analysis for high strain dynamic testing is an in-place real-time test. It's measuring the energy and the velocity of that hammer hitting the pile, and it's in real time telling you what the capacity is of that pile. And so it's confirming the weep analysis. It's confirming the drive criteria that's required for the rest of the project. And it's important. So when I say drive criteria, I mean, when we're out there and you're driving a pile to capacity, some certain capacity, say 500 kips, right? Let's say we're going to refusal. We say refusal at 500 kips, happens when your stroke of your hammer is at least 6 foot, so it's at least going 6 foot in the air, and it's the pile is moving less than, say, a half an inch per 10 blows. So that's what the weep analysis would tell you. We're confirming what that drive criteria is for capacity in real time. And so a couple of examples where this has been really important. One is the Chester Bridge. This is an ongoing project, a very big project in Missouri, big bridge that's crossing the Mississippi. The very first pile that we did on this project, contractor was forced to do PDA on all the piles so that they could use a thinner wall thickness, but he kind of thought, the contractor thought that it was pointless, that they were driving the refusal criteria. Everybody knows what refusal criteria is. It's when the pile stops moving and the hammer starts shaking, and that's refusal criteria. Why are we doing this? Well, the very first pile that we did, they drove to refusal. It's kind of hard to tell here, but they were not getting the capacity that was required on the pile. And the contractor is saying, we're at refusal criteria, we're done. We're gonna break this hammer if we continue to hammer this forever and it's not moving anywhere. And we said, you're not at capacity. And so we dug into the data, we started looking at the hammer performance, which is another advantage of the PDA. If you look at the hammer performance, and we said, your hammer's not performing correctly. We went back out and we hammered at a higher fuel setting, no change. We said, your fuel pump's going bad. And they humored us and said, okay, fine, we'll change the fuel pump. They changed the fuel pump. And it doesn't seem that significant. You can't hardly tell from the picture. But once the fuel pump was changed, they drove the pile an extra 4 inches before they got to capacity. Right? And you can imagine, had they gotten halfway through the project before their fuel pump failed, and all of these piles are at cutoff elevation, and they don't think anything of it, and then the bridge is built, and half of the piles, once under load, settle 4 inches, you're gonna end up with a pretty big problem. Bridge deck's gonna crack. You could potentially end up with a catastrophic failure of the bridge if half of your foundation settled 4 inches. So early in the project, we caught this, we identified this problem, changed the fuel pump, and now everybody's confident moving forward that drive criteria, refusal criteria is refusal criteria. Another example, this is the CRST building. This is in Cedar Rapids, Iowa. Again, the weep analysis was not accurate in multiple ways. What we determined was, theoretical capacity. We said, looking at the soils, the pile type that's being driven and the hammer they're going to use, we said, yes, the hammer is going to be able to drive this pile to capacity at a certain depth. Well, they have a hammer on site. They have all of their pile ordered, plus 5 or 10 feet. They start driving the pile, not getting capacity. They drive at full depth, not getting capacity. The hammer that they had on site was not big enough to drive it to capacity. It started to not drive the pile any further. So they had to bring on a new hammer, and then that hammer drove the pile full length and was still not at capacity. So then they're in a real dilemma because the project's been delayed already because they had the wrong hammer on site. They already have all of the material ordered. What do we do now? It's either going to be very expensive to start welding and splicing these piles on top of each other, or what they decided to do in this case was completely redesign at the 23rd hour the entire building. They took off a couple of floors off the top of the building, and they said, here, we're going to lighten the load, lighten the capacity across the board so that we can meet capacity with the material that we have on site and the hammer we have on site. So it was a big deal. But they said, okay, we're going to move forward with the foundation design, assuming this capacity, and we're just going to redesign the building to the different capacity requirement. But again, you could imagine how bad this would have been had they just done this based on the weep analysis, and then none of the piles and none of the foundations can meet the capacity requirements of this building. And all of a sudden, 5 years from now, the building is tipping out over the Cedar River and leaning like the Tower of Pisa, right? We'd have had a significant problem on our hands. So it might be 90% of the time where the weep analysis is accurate, it might be 99% of the time. That one time that the PDA, the in-place verification that we're talking about, saves you, it really saves you. And it's not that expensive of a test to run. So we have started recommending it on everything. At least do a test pile at the beginning of every project to verify that weep analysis. And the last thing we'll talk about here is actually there's two more, but load testing. So static load testing, this is on an in-place foundation. You can have a pile cap, but your foundation is in place and ready to go. We test this with a static load test. So we apply slowly a load with some hydraulic tools and a reference beam, and we apply a load to the shaft. Oftentimes we're going 200 to 300% of the design capacity, so pretty high loads, but we're incrementally increasing the load and measuring any sort of settlement or movement in that foundation. So you can do this both compressive or with a downward force or lateral, so you can pull it to the side just to make sure that this thing can take the loads that it was designed for. And there's a lot of different ways to do that. It's slow. It is expensive. You have to bring in special equipment to do it, but it's the truest method of, hey, this thing can take the capacity and the load that it was designed to take. One thing I didn't mention with the PDA is the big advantage is that can be done on a test pile if you want, or it can be done on a production pile. It uses the same hammer, the same equipment that's going to be there for the duration of the project. So nothing special has to happen. You just there and you test the pile. And you pay a little bit extra. Last thing then is this bidirectional O-cell testing. And this has been more popular in the last few years. It's expensive, it's specialty equipment, specialty contractors. But in this case, you put an O-cell in the shaft, oftentimes near the bottom. And you're able to test this to very high loads, upwards of 220 meganewtons of force. And the advantage is you can test both upward and downward and lateral forces on a shaft. So it's expensive, but this is a true measurement of load capacity, and some integrity information, because obviously if it starts to fail, you have an integrity issue. But kind of the truest method of actually applying a load to a shaft and testing multiple facets of the shaft's performance. Okay, I'm at 45 minutes. Conclusion here. I think I've said it multiple times, but your deep foundations are critical part of a structure. If they're recommended, they're there and they're important, and they're very expensive to install. And to date, there haven't been a lot of requirements for what does it take, what's the QA, QC, quality assurance, quality control look like on a drill shaft or a deep foundation. So we're doing our part to try and really push this, the industry to do more of the quality control, more of the deep foundation testing, at least require some sort of a standard for logging and inspection of the deep foundations. And remember, I always point this out, these foundations, if we are recommending a deep foundation, it's because the structures are critical and most heavily loaded structures, right? And so they're going to be the most catastrophic if something's going to fail. Your Walmart supercenter that's on a mat foundation of some sort, if it starts to settle, you get some cracking in the foundation, Walmart's probably mad at you. But if you have a high-rise building, or you have a bridge that starts to settle and that deep foundation starts to fail, it's going to be a catastrophic failure, right? So spending a little bit extra money on the QA, QC, recommending this type of foundation testing is critical moving forward. And there's tools available to do it. It's not like it's hard to come by. There's a lot of people that do the testing. And the technology is making it faster, easier, cheaper, and more efficient. Most of this stuff can be done remotely. Data can be sent to the cloud and be monitored from the office. So it's not something that's a huge expense or some big specialty thing that nobody out there can do. You gotta fly somebody across the country to test, right? It's easily accessible and we should be doing it all the time. Questions?
Question,
Yes.
so why are there only like certain projects you have to do it on instead of all projects?
Well, we're trying to make it so that all projects, require it. Right now, the DOTs are really the only consistent entity that includes it in the specs that you have to do. But there's a lot of commercial applications that don't require it. High-rise buildings, federal, buildings, hospitals. We're really pushing hospitals because that obviously would be a bad deal if a hospital were to collapse. But we're really pushing it on critical structures in particular, or sites where we're drilling and we're just like, hey, this is going to be really difficult to install a drilled shaft or an auger cast pile. You're gonna want a little bit of QA/QC on this thing. But it's just something that, for whatever reason, the industry hasn't really pushed too hard to require. And I feel like it's flown under the radar and been an issue for far longer than it should be.
So you guys only do it on DOT projects?
No, we do it on more and we recommend it on more. It's a conversation that we have oftentimes with structural engineers where we're like, hey, this is important, let's include it in the specs. And then it makes it into the design drawings as a requirement. But it's not oftentimes like built into any sort of IDC code or anything that you have to perform this test. So, yeah.
Question on the OSL testing, is that done on multiple piles on the project or just the testing pile?
Oftentimes it's only performed on the test pile. And then you could have different test piles in different areas. You don't just have to have a test pile at the very beginning. That's probably the most common. And it can be used on a production pile. So your test pile could be a production pile. But it's not usually done on more than a couple of piles. It's pretty expensive to do. And that one is a specialty thing. You have to really change your means and methods to install that one shaft that has the O-cell in it. You have to jump through some hoops to make it work more than a lot of the other tests.
I know that you said your company was advocating a lot for this testing. How do you guys, what kind of practices are you doing in order to, make this mainstream in the industry? So are there like conventions that you attend, or are there, something like that?
Yeah. So I'm part of DFI, which is Deep Foundation Institute. I've joined the American Drilled Shaft Contractors Association and Pile Driving Contractors Association. So I've joined a couple of associations and I go to some of their conferences and present on some of this stuff. The biggest thing that we've probably done is just start recommending it in our geotech reports. And we're not necessarily recommending the frequency, but at least that spurs a conversation. When the structural engineer reads our report, they say, hey, what's this requirement? Let's talk about it. And so then we talk about it and hopefully then it makes it into the plan drawings and the specs for testing during construction. That's probably the biggest thing that we've done is just, hey, we're just going to recommend it.
A follow-up to that question. Is there like a way, or in your opinion, that would best kickstart the industry to start implementing all these tests?
I guess if I had a magic wand, or an easy button, I would probably use it. I guess I'm probably doing what I think is probably the best. Joining the different associations, getting out there and talking to people and
Talking to college
students. Talking to college students so that the next generation of.
I know you said like the Department of Transportation, they typically do all these tests. So I imagine it's like these private firms that aren't necessarily making this requirement. So I was thinking like if federal organizations started implementing it, maybe that would be a way that these private corporations would also.
Yeah, the DOTs require it. And it's the public sector, I guess, and it's not required. So a lot of times they're gonna do the bare minimum and save a buck. So even if it's $10,000 or $20,000 to do this testing or whatever that looks like, and they're building a multi-million-dollar, they're gonna save the $10,000 if it's not required. So it really, it's largely on the geotech side, it's largely talking to the structurals, getting the structurals who really can put it in the specs, to include it in the design drawings as a requirement. That's been kind of our biggest push, but also where we've seen the biggest growth.
So is it really rare that you find piles that like need to be redone, or is it like common?
Like driven piles or
Yeah.
just, so driven piles, I would say majority of them are driven as expected. And they can look at that and they say, hey, we have a 45-foot pile. We expect to meet capacity at 43 feet and they're within 6 inches of it. But there have been a good amount of projects that I've been involved with where they blow right past 45 feet and everybody's saying, oh crap, now what? And so I don't know if I'd say it's probably less than 10% of those projects that the PDA really proved something wrong. It's probably more than that. It's probably more than that because there's a lot of projects where the bedrock's just variable and you have 3 or 4 borings on a project and you're extrapolating, drawing a straight line between the bedrock elevation and assuming that that's accurate, it's not. But as far as like the weep analysis just being way off, not just geology changing, it's less than 10% of those probably. But we do see issues with drill shafts and other foundations more often than we'd like to admit.
Is it common to have like faulty centers in the testing of the pile?
Is it common? No. Does it happen? Yeah. And that kind of sucks, especially like when we're doing a driven pile and they're in the middle of driving, nobody wants to stop driving until they're at capacity and I gotta stop the hammer because my sensor broke and all of a sudden I lost data. That stings. Nobody likes that, but it happens. You carry backups of everything so that you're not left with nothing. But I can count on one hand in 15 years how many times I've probably been on site and something broke.
Yeah, questions? There are a couple on the Zoom here. Well, I'm gonna ask this question first, then we'll go here. So, I'm a material guy and just stunned to hear that you rarely test them. Because when I was listening to your presentation, I thought like, okay, this thing is expensive, it's so critical. Then you're gonna test every single one. But you said no, not really.
No.
I'm really shocked. For example, this is my question though. I like your case study. I didn't know there is a story behind the picture. I thought it's just a pile, but I want to know that pile with all the drama behind it. How much money were you talking about?
That's a good question. I mean,
Roughly, put a number there.
I would bet you're spending, at least $10,000 for a shaft like that, but probably I would bet maybe quite a bit more than that.
Okay.
But I mean, they're expensive and you start to put 100 of those on a project,
Right.
It gets really expensive. We have a project that we're working on. It's a cancer center over in Omaha. And it has 180 12-foot diameter, 140-foot deep shafts. Like it's a multi-billion-dollar cancer center. And they're spending $1 million on foundation testing because it's a cancer center and these are huge, very expensive shafts. But I don't even know, like the concrete bill alone, it would probably blow my mind, the amount of concrete that they're putting in the ground out there. But I don't have a good number to put it that way.
Right. So in other words, the one that you're talking about, right? The picture, 10,000, then the test would cost you, if we do a test to guarantee or to verify it will work?
Oftentimes, like a tip test is maybe $1,500. You know, a CSL test can be as low as if we're doing it in mass, like we're doing a lot of it. There's always economy of scale, but $800 for a CSL test.
Because we're talking about this massive, you know, like how many miles of the power line, right?
Mhm.
So hundreds of them, and then we're talking about, you know, 1,500 each for one, so.
Yeah. And it
Okay.
really is, it's still like, we're pushing to make this standard that we do 10 or 20%. It's not very often that we test every single pile. And sometimes it's only, hey, let's just at least test the very first couple. Make sure that we get this thing kicked off on the right foot and we're not halfway through the project before we realize that we've been doing something wrong.
Because with my experience with concrete, I can tell you this. Compared to your skill, your importance, how much we test on concrete, you know. Roads. Right, you know, we test too much basically compared to what you are talking about. You should test way more than what we're testing.
Yeah.
With more importance.
Yeah, and we do a lot of, I mean, we're on, I don't know, I don't know if I'd say every, but we're on, we'll just say every project, testing concrete as it comes out of the truck, right? We're breaking so much, we're slumping concrete, we're testing concrete. And so we test a lot of concrete, but then they just kind of wave their hand or turn a blind eye on the foundation itself and say, it's good, the concrete's good.
Then the foundation is good.
Yeah, yeah.
That's a big assumption, right?
Yeah.
Okay, so we'll ask probably one or two questions and then we'll end at 6 o'clock officially. So here is, for the CRST project, essentially it was not the contractor's fault. The pile didn't reach capacity as originally designed. Did the geotech engineer or structural engineer receive a claim from redesign costs of the building? And from the owner having a smaller building than original plan?
I don't believe so, no. The WEEP analysis is theoretical. I don't think there was any negligence or anything that happened. Looking at the boring log, you know, there wasn't anything that was calculated incorrectly. It just wasn't reality when they got out there and started driving the pile.
So it's hard to point two fingers to who.
Yeah.
It's just the method was not.
Yeah.
Okay.
You know, you're along a river. There's a lot of variability in geology. So, you know, we had a lot of borings out there and you try and kind of take an average of all these for a single WEEP analysis to say that this is what's going to happen. And it just wasn't reality.
Okay. Second question is, are this deep foundation testing you mentioned about, are the engineers doing it or the technicians doing the test?
Oftentimes we will have, you know, some sort of a technician that is in the field doing it. But we have, like I said, a lot of this stuff can be remote monitored. So our pile driving, our PDA, you have to have an engineer certification. You go to take a course and you gotta have some experience. So we have our certified PDA engineers that are monitoring that remotely. You have somebody in the field that hooks it up and is there, but then they remote in and somebody in an office, an engineer in an office can be looking at that data in real time and making a determination of what's going on. The data's good. The pile, you know, stop something's wrong and then they're usually the ones that are communicating with the contractor via somebody in the field. Like I'm in their ear talking to them about what it is that we're seeing.
Okay. All right, the third question is very specific to this one. When using TEEP testing to determine TEEP quality, how do you differentiate between heat dissipation through the sides versus losing the heat through the bottom of foundation elements?
So, I mean, ideally, you're going to get heat dissipation on the sides and ideally relatively equal elevation all the way up. So if all of your wires at a certain elevation are doing something similar, you know, you can assume that it's due to the soil. So we look at it from top to bottom and you should see wires acting similarly. There's a calculation for roll off at the bottom that accounts for soil average soil temperature. And so there's an adjustment that happens at the bottom, and then there's an adjustment that happens at the top to account for that. And there's nothing that's really done for the sides, but there are some mid-shaft adjustments that can take place for when you hit the water table, or different soil conditions that might affect that temperature more. So there are some things that you can do to account for that. We need to be justified in it. We need to have something that shows up in the boring logs that says that, hey, this is why it's affecting the temperature.
Okay, all right, and then that's all the question I have here. So, well, it's 6 o'clock. You are all busy, so we'll do this. Let's thank our speaker one more time. Thank you very much. And then I believe our speaker will be here. If you have any questions, feel free to talk with the speaker, and then make sure you sign in here, so you get your PDH. And then feel free, if we have more food, feel free to eat all those food. Thank you again for coming. The next seminar will be March 4th on sustainable housing. Dr. Samia will be the speaker. So, well. Oh yeah, go ahead. Yeah, Judy, please, thank. Feel free. Thank you again to Turcom for the food. All right, so I'm gonna leave the recording here first. Very good, and then it will delete the file.
Make sure I get you a check.